going to start 2.4. This is a longer section, so we're going to kind of do a couple of things together. This is all about continuity, and I think this is going to take us 2 days to get through instead of just the usual one. So first of all, the word continuous, this means having no breaks or interruptions. So if we have a graph that looks something like this, where, say we got a point C, and that happens here, this would be a graph where we would say f of x is continuous at x equals c. So basically the graph is all kind of connected together. You would be able to draw it without lifting your pencil up, that sort of thing. If we maybe had a graph that did this sort of deal, it's kind of like a piecewise defined thing where we have a break in it at C. This one here would be discontinuous. So there's a lot of different ways that you can fail to be continuous and have a discontinuity. We'll kind of explore some of those in a little bit. So first we need to define what does it mean to be continuous. So we're going to define continuity. So we'll say definition, continuity at a point. So we say assume f of x is defined on an open interval So assume f of x defined on an open interval containing x equals c. Then the following things will happen. So we say then f is continuous at x equals c if the following thing happens. The limit as x approaches c of the function is the same thing as the output of the function for that input. So basically at c, what the limit approaches the same thing as the function value. That's what we mean to be continuous. So if the limit does not exist, or if it exists but is not equal to f of c, we say f has a discontinuity or is discontinuous at x equals c. So if the function is not continuous at a point, we would say it's discontinuous, or that there's a continuity. Couple things to note. A function can be continuous at some points and discontinuous at others. So, for example, up here we have a break in the graph here, so we're not continuous here. But if we looked at a point back here, this part of the graph here looks the same as kind of we had here where it's all connected. The left-hand limit and the right-hand limit exist, and they're approaching the same thing as the function value. So we would be continuous over in this region, but we're discontinuous where we had that jump, we could say. So that's just a handy thing to note. Also, if a function, if we're looking at an interval, if we look at an interval, say close bracket a up to b, or close bracket a up to open bracket b, we say, well, we're supposed to be defining continuity. We said we had to have this open interval. What about where the interval, one of the intervals we're looking at, the function stops there? How do we define continuity there? So if we have these where a is an included left endpoint, then we require we require that limit as x approaches a from the right hand side. So you're going to approach a from the right hand side, which is approaching it from the inside of the interval. So as long as the limit of your function is equal to the function value at that point, you can be continuous. Similarly, if we had a up to b, or a open bracket a up to a square bracket b, and we wanted stuff to be continuous, we would want the limit as x approaches b from the left of the function to equal the function's output at that b. So this is, we'll talk more about these with an example, but this is kind of how you handle whenever you're, if you have like a square root graph and you want to talk about continuity and the graph kind of just stops here, doesn't exist beyond that. This is kind of how you can talk about those sorts of things, which we'll do some examples to make this make more sense. So basically, for continuity, you need the limit of the function to exist, you need the function's value to exist, and you need those two things to be the same at the point. So we're going to focus on just our first example or two from this section, and we want to show the following are continuous. So part A, we want to show f of x equals k, where k is some constant. And part B, we want to show g of x equals x to the n. Now, when you say you want to show a function is continuous, so we defined continuity at a point. So this right here was continuity at a point. A function is continuous if you can show for every point in its domain the function is continuous, then we call it a continuous function. So basically what we need to do to show it's continuous, we need to show the function is continuous at all points. That's what it means when you say show the function is continuous. That's what it means to show. So instead of like plugging 1 in, then 2 in, then -1 in to try to show continuity at each of those, there's infinitely many numbers, so you're going to have problems doing that. What we'll do is we'll choose kind of an arbitrary value like c or something like that. And if we can show that this is true at x equals c, and c can be a stand-in for any number in the domain of the function, then we can get continuity of the function that way. So there's kind of 3 steps we need to show. We need to see, first of all, what is f of c. So I'm looking at, usually evaluating the functions, the easy part. So I'm looking at what is f of c. This is the right-hand side of this equation here. So f of c, well, f of x is k, so f of c is k. Okay, so then the second thing we need to do is we need to see what is the limit as x approaches c of f of x. So we need to figure out what is this expression here, left-hand side. Then we want to state that they're equal at the end if they are. So limit of f of x, x approaches c of f of x is k. This is limit as x approaches c of k. And the limit as x approaches c of k, that's back from our theorem back in section 2.2, I think. This might be 2.1. This is just going to be k. So these two things are the same, so we are continuous, and we'll write it up as the limit as x approaches c of f of x equals f of c, and those both equal k, so we have our function is continuous. We showed the two-sided limit here, limit as x approaches c of f of x, is same as the function value. They both happen to equal k. So everything checks out, so our function is continuous. And since we didn't define what c was, c can be any number. So this will hold for c is 2, this will hold where c is 7, this will hold where c is negative 3.1. So we've shown that f of x is continuous. So over here we want to do the same thing. Say first of all, what's g of c? Well, g of c would be c to the nth power. And second, we need what's the limit as x approaches c of g of x? Well, that would be the limit as x approaches c of x to the nth power, which will equal, if we go with that, x to the nth power, we could use our equation or our stuff from last time. We could pull the limit inside of the nth power and get limit as x approaches c of x. This will also be c to the n. So these two are the same. So we can write this up. The limit as x approaches c of g of x is equal to the function value g of c, and those both happen to equal c to the n, and this shows the function g of x is continuous. So we're going to look at different types of discontinuities. Actually, you know what, let's do that in another video. Let's stop here. This will be a good little bit, and then that way you don't have to hunt through a 20 or 30 minute video. Okay, so I'll pause there, and we'll get types of discontinuity stuff in a minute.